what a maximal domain is for certain functions, they aren't able to take certain values just because of that's how they work and how they're mathematically defined. So when the domain is not stated, you can always assume that the domain is the maximal domain. So like for the previous question, the domain was stated, so you just have to go with that domain rather than the maximal domain. So for polynomials, the maximal domain will be R, just like we saw for our parabola just then. We can really input any values in and they would still work. However, for some functions, you can't really use the same thing of R because there are certain values where if we tried to put that in, the function would be undefined, right? And it's just mathematical type definitions and you can kind of figure it out from there. Two of the main ones that will be coming up quite a lot is going to be the 1 over x and x squared. Oh, sorry, not x squared, square root of x. So let's think about both of them, but let's think about our 1 over x first. So our 1 over x, right? If we think of how this function kind of looks like, we know that this function kind of looks like this, right? And it has asymptotes along here. Oopsies, that's really wonky, but I don't know if it's right, whether should we redraw it or not. I'll redraw it, that's okay. Try to redraw it with better asymptotes. Cool, awesome, alright. Oopsies. Oh my goodness. Drawing parabolas is always fun. Okay, finally. Alright, so that's kind of what it looks like. And we can kind of see that there are going to be asymptotes at x equals to 0 and y equals to 0, right? So what we see here is we can see the asymptotes here. And with asymptotes, that evidently means that one of the numbers won't be able to be accepted. So what we're going to do here is we kind of think of it mathematically, like what wouldn't work with this function, right? So we can kind of go through all the values in our head of what wouldn't work, and we kind of figure out that 1 over 0, right? 1 over 0 to us is going to be undefined, as we would know. So it's going to be undefined, which kind of gives us a little problems, right? Because that kind of corresponds to what we think our function looks like. So that's going to be undefined. So essentially what you're going to do here is that anything in the denominator cannot be equal to 0. So when you have a function like 1 over f of x, right, you're going to actually try and solve for f of x equaling to 0 to really actually find the asymptotes and where they're located. And that works for any function you basically put at the bottom. And even when we have like when we have quotient functions where we have like h of x over g of x, what we can try and do is find what the factors of the g of x are, i.e. we can solve g of x equaling to 0 to kind of actually give us what factors can't be included. And I guess this is a bit of a fun fact which might come up in quite a tricky and exam 1 question, but if you have hx being able to be divided by g of x, so for example if you had a common factor between the two, so the factor would cancel out top and bottom, but there would be an empty circle left there because in the original function it still wouldn't be part of the function overall, right? Because it would still make the denominator 0. So we just leave an empty circle there rather than actually putting something in. Cool. Alright. Let's talk about root x. So we think to ourselves, alright, with root x, we have to think what under a root would not be defined, right? So if we kind of go through our number system again, we think, okay, broadly speaking, we think about positive numbers, right? We're like, okay, positive numbers work. What about 0? Because 0 was the problem last time. Okay, 0 should work because root of 0 is just 0. Okay, what about negative numbers? Oh, that doesn't really make any sense, right? Because no number squared is actually going to give you a negative number. That is subject to us not working in the complex plane, obviously, but we in methods work just in the real plane, and we just keep it that way, and we don't need to consider anything outside of the real plane. So what we kind of do is we say, all right, so that means that negative numbers can't be included, right? So we're going to say to ourselves that therefore the square root cannot be less than 0. So in reality, what that means is if we had a root of f of x, we would have f of x is smaller than 0, right? And then we would just solve for that and exclude all of those values. And yeah, because it's smaller than 0, also that means that you'll, one, have to graph what f of x by itself is, right? Especially if it's not a linear function. And 2, you'll actually have to solve f of x equaling to 0 as well, because you first need to find values before you can kind of decide which side of the inequality it will be on. Alright, a couple more that we want to chat about. So logs and tans, they are kind of black sheep of their own families, but they're useful ones to know, and in fact I find that those two functions are quite useful in a lot of aspects. So let's talk about our log first. So if we consider the graph of what a log looks like, it looks something like this, right? That's what our log looks like. So right away from our log, we can kind of immediately tell that we're going to be working with numbers kind of 0 to infinity, right? Well, 0 to infinity, not including 0, right? But if we didn't know what it looked like, we think of a log as a power, right? So if we had a power which was infinitesimally very small, as in very almost negative version of small, or if we had like a 1 put in here, right? Because this is essentially going to be the original kind of like power complex, right? Because remember, if we have e of x equaling to a, then we have log ea equaling to x, and this was the original output. So if we mean that, that means that e of x, right, has to equal to something. So e of x has to be able to be equal to that something, right? Oh, sorry, e of whatever the thing is, let's say e of a has to be able to equal to x. But we can see that e of x, right, as a function, it never touches 0. So that means that x cannot be 0, right? And it never goes on the negative side. So that means x cannot be negative either. And essentially when we get a negative log, what we're implying is that something to the power of something equaled to a negative number, right? And because we're working with like all positive numbers currently, so we're assuming, we know that e is positive, it's like 2.7 something, and we're assuming that, I guess you can try to not assume that x is positive. So if we try to pretend, all right, let's try and find out what's going on here. So if we did x is positive, then all is happy, we get this side of the graph. If we tried when x is negative, what that actually means is that e to the power of something, whether positive or negative, so it could be e to the power of -1 or e to the power of 1, right? That's going to equal to a negative number, which we can tell is not possible, right? Because even if you put an exponential to a really, 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 really big negative number, it's not going to turn negative. It's just going to become infinitesimally small instead. Cool. Alright, so let's talk about our tan function as well. So tan function, once again, it does have asymptotes. And why we have asymptotes, it kind of comes back to our 1 over x type theory. So tan is sine x over cos x, right? And if we kind of use our 1 over f of x, where we need to solve for f of x equaling to 0, what we're trying to solve for is cos x equaling to 0, right? And because it's going to repeat every period, we really only just need to find 1 and then add or subtract periods from it. So we know that cos x will equal to 0 at pi on 2, because kind of if we consider that unit circle, we can see it hits exactly 0 up there. Cool. Awesome. So for logs, the number inside the log must be greater than 0, and for a tan, the function cannot be any n pi over 2. I guess that's also like with the pi n over 2, it's a kind of subjective thing where, not subjective, that's not the right word, kind of like, so if you had 2 pi, right, 2 pi over 2, that would equal to pi, and that cause a number. So in fact, instead of saying this, it should be more like 2n plus 1 pi. Oh, sorry, not 2n plus 1. 2n pi plus pi, right? Or pi 2n plus 1, right? Because it's all the odd numbers of pi is what's really actually going to get you the 0 down there. So just be careful about that. Okay. Alright, so let's move into chatting about a question now. So when we look at this question, let's have a go together. So what we want to do is we want to find the maximal domain of this question, right? We have two kind of components to consider here. The surd up the top and this denominator, right? So what we can do is actually just consider them separately and then bring them together afterwards. So what we know so far is from 1 over x, the bottom cannot equal to 0. And if we're talking about a square root, this part has to be bigger or equal to 0, right? So what that means is x minus 9 cannot be equal to 0. So x cannot be equal to 9. Cool. Alright, with this one, we're thinking, alright, so that's x minus 1 has to be greater or equal to 0, right? Greater or equal to 0. So what that actually means is x will have to be greater or equal to 1. Okay, so now we have these two types of conditions, and what we want to do is kind of conjoin those two conditions together, right? So we have x is bigger or equal to 1 and x does not equal to 9. So what we can do here is, there's kind of two ways you can kind of write it. So you can either write 1 to infinity union, excluding 9, or you can write it something like 1 to 9 union with 9 to infinity. Okay? I think this one's a little bit more difficult to write in kind of set notation or inequality notation, just because the not equaling to 9 is a bit hard to express without using these symbols in between. But it is up to you what you want to do. Right here.